We're now going to discuss the speed of waves on a string, which is section 13.9. All right, let's move this over. Let's now turn our attention to the speed of a transverse wave on a stretched string. For a vibrating string, we need to consider two speeds: the speed of the physical string that vibrates up and down transverse to the string in the y direction, and the wave speed, which is the rate at which the disturbance propagates along the length of the string in the x direction. If a horizontal string under tension is pulled vertically and released, it starts at its maximum displacement y equals a, and takes a certain amount of time to go to y equals negative a and back to a again. This amount of time is the period of the wave and is the same as the time needed for the wave to advance horizontally by one wavelength. Dividing the wavelength by the period of one transverse oscillation gives the wave speed. Oh, got to be on the there. V equals lambda divided by t. Consider the situation where the wavelength is a fixed length. Then a string under a greater tension has a greater wave speed because the period of vibration is shorter. Remember that the wave advances one wavelength during one period. It also makes sense that a string with greater mass per unit length, mu, vibrates more slowly, leading to a longer period and a slower wave speed. Just think of the lower notes on a guitar. They're usually thicker, and they even have wire wrapped around them. There's more mass, so they move slower. The wave speed is given by the expression shown here. V equals the square root of f minus u, where f is, well, I'll just read it. The wave speed is given by the expression shown here, where f is the tension in the string and mu is the mass of the string per unit length, called the linear density. From this equation, we can see that a larger tension results in a larger wave speed, and the larger linear density gives a slower wave speed, as we expected. So if you tighten a guitar string, you'll get a higher speed, a higher note. According to our equation, the propagation speed of a mechanical wave, such as a wave on a string, depends only on the properties of the string through which the disturbance travels. It doesn't depend on the amplitude of the vibration. So we can increase the speed of a wave on a stretched string by increasing the tension in the string. Increasing the mass per unit length, on the other hand, decreases the wave speed. Okay. So one slide discussion.